Hello, everyone. Welcome to the Icahn Skills and Development Seminar. We are we should start soon. So today we have with us Jeff Goldsmith and Elena Colicino telling us more about the emergence and the beauty and the future of data science. So before we begin, those of you who have not heard of Icahn, the group which is holding this online event before, I mean, some of us may have some questions like, what is it? So Icahn is actually a community of professionals designed to help each other with career and skill development. Whether it is entering the workplace or breaking into a new industry, the group Icahn, powered by volunteers, can provide resources to allow everyone to learn, share, and grow in their careers. If you're already here, then you probably have gone through the Eventbrite, which has some email information about how to reach us, and we'll also let you know our email in the private in the chat here. So, with this spirit, I'd like to introduce our today's speaker. First, we have with us Jeff Goldsmith. So Jeff is an associate professor in biostatistics at the Columbia University Icahn School of Public Health. And we also have with us today is Elena Colicino. Elena is an assistant professor at Icahn School of Medicine at Mount Sinai. So both of them will be giving us today some description about the very essence of data science. Some of us may have questions like, why do we need it? What is it? How does one go about exploring this? So experts like Jeff and Elena will tell us more about this. So some housekeeping rules. We'll begin our event today by first hearing from Jeff about his take on this topic. Then there will be a few minutes of questions. Following that, we'll hear from Elena, and then there will be some questions on Elena's presentation. And then we'll have some joint conversation between the audience and our speakers. So for now, other than the speakers, everybody else is muted. Please kindly type your questions in the chat option here, and we will highlight your question to the speaker at the end of the presentation. So without much delay, I would like to give the floor to Jeff, who will be telling us more about the emergence and the future of data science. Jeff, the floor is yours.
Great. Thank you very much. This is a pleasure to be here and have the opportunity to chat with everybody this evening. I'm going to go through some slides relatively quickly. Let me make sure I can share these. Let me know if you can't see my screen. I think everybody probably can, though, as I switch to slideshow. So I'm gonna try to run through this relatively quickly and describe, at least for now, what my view of data science is and where I think the field is going. And then along the way, I'll give some ideas about how you might learn more specifically how to engage in and do data science. And the first thing that I want to point out is that if you are unsure what data science is, that is entirely reasonable in the sense that it is a new term. It is something that has become very popular very quickly, but that didn't exist really 10 years ago. So this is a Google Trends chart showing from January 2004 up until roughly 2018, what happened when you typed data science, or how frequently people typed data science. And they just really didn't, even through 2012, 2013. I finished my doctoral program in 2012, and at that time, data science hadn't even really caught on. So the fact that this has sort of sprung to such great prominence in such a quick time either could be a sign of boy, just some sweeping idea that we really can't get a firm grasp on. But I think it really, despite that sudden prominence, is underpinned by ideas that have been around for a while and that are recognizable, but have been sort of combined in a way that is new and interesting. And so when I say ideas that have been around, I want to sort of talk about, at least for me, why I think data science emerged as quickly as it did and as forcefully as it did. In the run up to the emergence of data science, folks in academia and in industry were talking about 4 related but distinct trends, things that have to do with the emergence of big data, either because data sets individually were getting larger or the ability to gather data on many people simultaneously was becoming easier. There was a switch from traditional statistical approaches and things like p-values more towards an emphasis on the ability to make predictions, specific predictions about individuals, whether that's in industry through targeted advertisement or something like this, or in medicine through precision medicine, identifying the right treatment for the right person at the right time. Another trend is, at least in science, a reproducibility crisis. And what I mean by this is, especially around the emergence of a paper that argued that most published research findings are false. It's a bold claim, but it's one that really shook the scientific community and put energy around and put emphasis on the ability to both publicize and disseminate the work that you're doing and ensure that other people can obtain the same results. And then the last broad trend is a shift towards interdisciplinary work. The idea that no one person, no matter how skilled they are, no one person is going to be able to make the advances that are necessary in the context of solving some problem. And so each of these trends, I think, weren't new in 2012. They've been around for a long time, and they aren't unique to data science. But the sort of confluence of these all at once, I think, gave rise to a perspective that is apparent in data science that maybe I think is new and different. You almost can't define data science or think about defining data science without seeing this image. And I think it is a useful place to get started, at least in part because it gives some idea about what ideas are relevant to the data science community. And so this is a Venn diagram from, I think, 2014 that says one bubble is math and statistics, sort of traditional work. One is substantive expertise, I think, driving home the idea that you do need some interdisciplinary collaboration, but then also hacking skills, where hacking skills is a broad definition. Maybe it includes some amount of reproducibility. Maybe it has some facility, some ability to work with big data. There may even, when you combine these two areas, give you some idea about what precision might look like, about an emphasis on prediction is. And the idea is that if you combine all of these things, at least in this image, the idea is that you sort of arrive at data science. This is, like I say, at least 2014 in the context of data science is, a little bit out of date, but it does give you an idea about what people have sort of gathered around, what sort of the coherent principles for defining data science might be. Now, I also want to take a step back, and even though I am going to pose the definition of data science that I prefer, I am going to be clear that there isn't one single definition that is universally agreed upon. When I talk with colleagues in a computer science department, for example, they have a very different opinion about what's important in data science than, for example, I might. And this is, I think, fair. We're talking about something that is not, I think, a single discipline, but something that has its own unique characteristics, but also is broad and diffuse. So there may not be ever a single definition, but that doesn't mean that it's not something that we can get our hands on. I'm gonna, again, before actually offering a definition, I'm gonna draw on a parable and then make an analogy to sort of, again, give an idea of what I think data science is. So there's a parable that I've become familiar with recently that is, if you asked some blind men to stand around an elephant and reach a hand out and sort of describe what it is in front of them, those descriptions, I think, would be subjective but accurate depictions of what an individual is experiencing. And there's no real reason to argue this definition is wrong or this description is wrong or that description is better. They're all sort of fair in as far as they go, but they're not really going to give you a sense of what sort of a big picture is. And I think especially early in data science, when folks were saying that data science is either just statistics or just big data or just computation or just something else, I think they were accurately describing one small piece of a very large puzzle, very big thing that is data science and is sort of hard to grapple with. That said, although these individual competing sort of local descriptions of what data science might be are all well and good, they are also not going to sort of give you a complete picture. They do sort of tell you local structure. They tell you things that are important to a data science community, and I'll expand on this in a minute, but things like using data in a principled way and doing it in a way that is clear and transparent and based in a good understanding of how to write code. So that's my parable in thinking about data science as like a big multifaceted thing that is difficult to describe. The analogy that I'm going to use comes from transportation. And I didn't come up with this analogy any more than I came up with the parable, but I like this analogy because it sort of gives an idea both about the local structure, sort of the very specific things that data science might be interested in, but also the broad and diffuse impact. So around the same time, two things were happening in transportation technology at the beginning of the 1900s. First, there was the first flight, which was a bold advance in transportation that was available to a very small number of people. It had huge potential. It has downstream, decades later, led to an airline industry. But in 1903, it was very, very advanced and very, very localized. And about the same time, automobiles were going into mass production and made real advances in technology available to a much wider group of people. And so in drawing this analogy to data science, I sort of think of things like the AI and deep learning work that Google is doing, because Google has all of the resources and all of the data, is absolutely doing data science. But at the same time, the general trend towards better data literacy and improved tools for visualization, that is also a real contribution to data science. That both of those things are, they advance the state of what data science is capable of doing, certainly in very different directions, but both of them I think should be thought of and recognized as advancing data science. So I am going to offer a definition, even with the caveats that I've given up to this point. This is sort of a blending of a few other definitions that have floated around, but I think of data science as the study of formulating and rigorously answering questions in a data-centric process that emphasizes clarity, reproducibility, and effective communication. So there are a variety of things that are baked into there. What does it mean to formulate a question? How do you rigorously answer a question? Is exploratory analysis enough? Do you need statistical testing? Is that a prediction approach? What does it mean to collect data that support or don't support the question that you're interested in? Beyond a data-centric process, that's sort of a very vague term. There are a lot of things in there that could be unpacked in quite a bit of detail, but the idea that I have is from the beginnings of thinking about a question until you produce some result that you hope answers that question, at least in part, the different pieces of that and learning to do each of those components well all sort of counts as data science. And the rigorously answering questions, this could be a big data problem, it might not be a big data problem. It could be a prediction problem, it might not be a prediction problem. But the way that you think about this, I think, is important. I also, an approach that I have had recently to sort of trying to defend this definition of data science, trying to defend data science in general, is to get the idea that there are definitions for words and there are also connotations for words. So many scientists would look at this definition of data science and say, that's what I've been doing for 20 years. That's what I did well before 2012, well before data science existed. And I think the response that I have for that is, in part, yes, but the connotation here of data science has to do with things like, how much do you care about reproducibility? And are you aware of big data techniques? Is there some collection of values that you place on how to do data analytic work in a way that is clear and reproducible, that is sort of consistent with what is recognizable to a data science community? I think that connotation is in some sense as important as the definition. So I'm going to talk a little bit about tools for data science, what makes a data scientist, and then a little bit about how you can learn some of these things. I think what makes a data scientist in general is a willingness to engage in problems. I think that although you do have to be interdisciplinary in the work that you are doing, and I don't think any one person is going to answer all of the issues that arise in a project, it is important that everybody engaged in that project is interested in finding some solution, is engaged intellectually and curious about what's happening. I think being a good data scientist, again, this is more about connotation than definition, but is using tools that are appropriate for doing data scientific work. And I'm going to expand on that point in particular in just a moment. I think it's important to be familiar with a range of analytic choices. And by range of analytic choices, I mean things from t-tests and drawing graphs and exploratory statistics to aware of, if not an expert in, modern approaches to doing supervised learning or something like this, to doing a more complicated big data approach, and sort of being aware of what that range is and being able to choose what the right tool is. And then lastly, a sort of sense of being able to use data appropriately and think quantitatively. And I'm gonna touch on those last 3 points in the next 3 slides. So the first is to use tools that encourage success. This is a figure that I like a lot for making this point for 2 reasons. The first is that the slide in the background, I think, drives home the design principle that I'm speaking of. And the other reason is that the person sort of mimicking doing data science in the foreground is a person, Hadley Wickham, who has developed an awful lot of these tools. So the principle that he has for designing tools for doing data science is that rather than thinking of success as a hard, difficult process climbing to a peak of success, it would be much better if the tools that you use make it such that you fall in, that by virtue of gravity, by using the tools that you care about, you fall into being successful in terms of transparency and reproducibility and best practices and clarity and things like this. So choosing the right data science tools, and I'm not advocating for any one collection of tools in particular. I use R in RStudio and the Tidyverse, and I think that is one that really does encourage success. There are other frameworks that you could use also, but sort of start out and choose the right tools. The other thing that I wanted to talk about in terms of a range of analysis approaches is that although data science has become in some sense not synonymous with AI or deep learning, but certainly that is where many people go, when we start thinking about what data science is, often in the back of the mind of somebody who is really doing data science is the idea that certainly I could use AI, I could use deep learning to solve this kind of a problem, but also machine learning, which is maybe one step below AI on the scale of technical difficulty, that probably will also work, and that might actually be what we end up having to do. And then even one step below that on the sort of level of technical difficulty, there's good old logistic regression, a framework that has been around for decades, and that might be the analytic approach that is the most appropriate thing to use. And it's sort of one that I think most data scientists recognize as true, is that there is in fact this spectrum, and we have to sort of find where on that spectrum of tools we're going to use the most appropriate thing. And then the last point that I want to make before a couple of quick tips on how to learn to do data science is to think about a general data sense, right? So data science, big data, AI, things like this don't solve perennial challenges that exist in data. And what I mean by this is a sample that you have that is biased and doesn't represent the people who you care about isn't going to give you good answers. If you have confounding effects, without sort of going into what I mean by confounding, but if you have a lot of variables and they're all sort of correlated with each other, understanding which is an important variable and which is one that just sort of happens to be associated with an important variable, that's a hard problem, and that doesn't go away just because you have big data. Knowing whether or not an effect size is actually meaningful is going to be up to at least some judgment that you have to make. If you're trying to identify correlations versus causations and how you actually make those claims, those are hard problems, again, not solved by AI or big data or other things. And then finally, whether or not the work that is being done, especially, I think this is important in the context of big data, mass surveillance, tech companies scooping up all the data that's possible, whether or not the approaches that are being taken are actually ethical, the right thing to do, I think is an important consideration. And I'm going to skip past that figure just in the interest of time. So I think I want to sort of end by giving some idea about what you might do next. And although we don't know what data science is going to be, I think there are some ways that you could prepare for what data science is now and what it is likely to be in the future. And I think starting out by getting a broad foundation in both data science tools and in existing analytic approaches, sort of the Model T level of things, getting that level of proficiency is important. And I think there are a variety of mechanisms that you can do that. I think there are online resources, there's Coursera, there are boot camps that are in shorter terms, there are more formal, part-time, full-time degree programs, things like this. I'll point out and do a quick plug. I have a course that teaches how to do R programming, and all of that material is online and freely available. The other thing that I would recommend is to build an awareness of modern approaches, and that is a little bit different from saying you need to be an expert in unsupervised learning, but I think you should have some sense of what these approaches might be and when you might use them. And the data science community, I think, has taken several steps to be active and inclusive and engaging, especially the R user community and various community forums and meetup groups, conferences, seminars, things like this. I encourage you to sort of participate in this. If you have some existing work that you have done in a different sort of framework, if you have old analyses that you have sitting around, I would challenge yourself to try redoing those from a new perspective. You know what the right answer is. Try coding it in R instead of in SAS, for example. Try a different analytic approach and see if you get similar results. And I think that's sort of where I'm going to stop and turn things over to Elena. I am going to put up my contact information if you have any more questions. And as I said, do a plug. The course that I teach, the course code is P8105, and if you go to p8105.com, all of the course materials are available online, and I'm sort of recording video lectures for this semester and putting them up as I go. And with that, I'm going to go ahead and stop and say thank you very much.
Wonderful. Thank you, Jeff. It was really wonderful. It was you gave a very great overview of the whole very complex field. So so those of you who have joined a little bit later, if you have any questions, feel free to write them in the chat option, and we will have some time for some Q&A. Okay, so we have our first question. So what kind of career advice would you give to young people who are interested in data science? Is a master's degree necessary to excel in the field?
I think that's a good question. I don't know that a master's degree is necessary. I think some degree of formal training, I think, helps, right? I think data science is an area where you can learn an awful lot based on online resources, but there are some gaps in the knowledge that would exist. So I do tend to favor, just as a general principle, some kinds of formal training, but I think data science is unique in the sense that most data science groups, companies, are as interested in your demonstrated skill set as they are in whatever sort of credentials you might have. And a demonstrated skill set is something that you can get in a variety of ways. I think there are a good number of folks, for example, who have taken Coursera courses, and I think the Johns Hopkins biostatistics department has a specialization that is widely regarded as very good, who do that sort of a thing and then do a few projects, put them online on GitHub so that it's publicly available and you can demonstrate some proficiency to an employer. I think that is a viable route. Again, I'm not going to say necessarily that that's the best or the only one. I teach a master's course, and I think it's really useful for the students that I have. But I hesitate to say necessary to excel, only because that so much of the resources are available online.
Okay, so so for those who might be teaching student data science, like since you are doing it, so do you have any suggestion for skills, platforms, or language that will be relevant for 5-10 years down the road?
Yep. So I think there are a few recognizable data science platforms and languages, and which of those you choose is a little bit up to you. I think if you were going to argue that Stata is a good data science language, I don't think that would be particularly a great perspective. But I think if you were trying to decide between, say, R and Python, either one of those is going to work reasonably well and be recognized as a sort of bona fide data science language by the data science community. My preference, largely based on my own background for doing data science, is to use R. And partly that's because R was built as a statistical programming language and has a lot of the things that you need for interactive data analysis built in. Python was designed as a scripting language, as sort of a computer science language. And it probably is better for some kinds of machine learning. But I think in either of those cases, whether you're going to use R or Python, I would recommend that you use recent tools. So R, use the tidyverse and use R Markdown and things like this for reproducibility. And if you're going to use Python, use sort of the analogous Python tools that you might use. And I think those are established enough now that they will be relevant in 5 or 10 years. Absolutely.
But also, Jeff, I mean, this is like one of my questions. Also, the language or the platform that you use, it always updates, right? I mean, after 5 years, you might find something, some really exotic, some really nice user-friendly platform that which you would want to switch to, right? So things change.
It's true. Things do change. If I had to make a prediction, I am going to guess right now that the kind of code that you might write in R today is going to be broadly similar to what you might write a few years from now. And I feel like that is a bold prediction, but it's one that I'm willing to make because folks have spent a lot of time, in contrast to say 10 years ago, folks have spent a lot of time thinking about how you should do data organization and manipulation and analysis. And I think starting from those design principles and then embedding that in a language has made that language more likely to be used in the future than things that were used in the past.
Okay, thank you. If we will have some more time for some discussion later, so we will now go to Elena, and after Elena's presentation, there'll be time to again ask questions to both Jeff and Elena. So thank you, Jeff. Okay, so now we'll have Elena telling us about her take on the data science.
Hi, everyone. Actually, thank you, Jeff, because you gave a definition of data science and I didn't, because I was puzzled with all the definitions that we have in the literature. Can you see my screen? My presentation? Hope so. Let me know otherwise in some way. So actually, this is my point of view of data science, and I started from the objective of data science, which is actually understanding and describing what we have in the reality. And actually, the reality is represented by data. So all the data require a lot of attention, from collection, organization, and then analysis and visualization. So once we go through this long workflow, rigid process, data can help us to take better decisions. And this is why I consider data science a branch of the decision sciences. I actually graduated in a program of decision sciences in 2012. So this is why I'm considering in that way. So all people that manipulate and or handle data are considered data scientists, and everyone is helpful because we have different skill sets, and often those skills are complementary. So this is why everybody is needed in this kind of field. And here we have 3 data scientists, and here a brief description of all of them. So first, we have data analysts that apply models and visualize data. So they are specifically focused on that. And then we have data engineers that are responsible for the data architectures and uninterrupted flow of the data. So they are actually highly in demand, and I don't know many of them, especially in academia. We have a few of them, and they are responsible for the entire data set that we have. And then there are statisticians that are mostly focused on creation of the models and adaptation of the model to the real data. So of course, I can provide that perspective. Here is actually the workflow, and I think it's a very rigid workflow about the data. So usually data start from collection, acquisition, and and in visualization. So after visualization, we take decision. Here we have our 3 data scientists, and each dot represents the workload of each data scientist, and the size of this dot indicates the workload. So the bigger is the dot, the bigger is the workload. As you can see, the data engineers have heavy workload, especially at the beginning, especially with data extraction and enrichment. They are mostly focusing on reconciliation, which is a very difficult topic, while data analysts and science statisticians are mostly focused on the analytics and the visualization of the data. One thing that I want to mention is that all the data scientists spend a lot of time on cleaning data, and this is a very important step to have good modeling, also predictions, and visualization of the data. So this is why all the 3 data scientists are having on data cleaning and enrichment here. Today I'm going to talk about data analytics mostly, because it's my perspective, and statisticians are mostly focused on that. So, as I said, the statisticians are mostly focused on creating and adapting models to real data, and statistical models provide a summary of the data, because what we want is describing and understanding the reality. So the more complex is the reality, the more complex is the model. And the more complex is the model, the more data we need. So this is why we always say that in God we trust, but all the others has to bring a lot of data. So if we want to understand and describe the reality, our method should mimic the decision processes that are used in real life. At least this is my opinion. And those models should not include only data, but also our thoughts, opinion, and prior knowledge. And in that case, we can do with some Bayesian methods. So because I know that it's almost 10 p.m., I wanted to do it in a very light way, and I'm going to use Disney character for that. So here we have Uncle Scrooge that wants to go on vacation, and he wants to hire a person to protect his safe. So he posted a job, he has an opening, and he collected a lot of resumes. Among the resume, he picks one, and he look at the resume, and what is written on the resume are actually facts, things that already happened, and those are also known as data. So in this case, he picked Mickey Mouse resume, and he had very high grades when he was in school, and he was a policeman. So he's the perfect candidate for this job. And when we take decision based only on the data, basically we are doing just classical statistics. But actually in the reality is not like that. It's even more complex, especially in academia. We ask for references, and when we do that, we actually updating our information. We are updating our results that is coming from the classical statistics, and we basically create a new result. And in this case, the references are very supportive, and they say that Mickey Mouse is very collaborative, precise, and so is the perfect candidate for the job. However, it's true that we have references that can be good, but in other cases we can have references that can be also bad for the candidate. And in that case, we can update the results that we would have just looking for from the data, and we can take a better decision here. Just for complete the story, I want to give you also this information when references don't give a lot of information. In that case, those references do not change our results. And basically Bayesian statistics is equivalent to classical statistics. So saying so, one thing that I want to remind ourselves is that all statistical models are a summary of the data, and so there are always some observations that don't follow the model. And this is actually extremely important when we do prediction or machine learning approaches, because especially when we train, so when we create a model in a specific population and we want to create adapt that model, so use those results in a different population, we have to make sure that the two populations are quite similar to each other. Otherwise, we can have a lot of errors there. So in my case, I mostly use Bayesian methods in environmental health to understand the effect of multiple chemicals on human health. And here is a description of a mixture. So here we have jelly beans separated by colors, but also jelly beans overall. So for me, jelly beans bring happiness in my life, and I don't care if they are red or green. I'm interested just eating of them, all of them. So most of the time, scientists used to test one single environmental chemical at the time and evaluate its effect on health. However, this does not represent the reality, because every day we are exposed to several environmental chemicals. And as I said, we are interested in understanding if one of the chemicals is most detrimental than others, and how much of the overall mixture is linked to diseases. So I can give you a brief example. So in this case, low birth weight is linked to childhood obesity and poor aerobic fitness later in life. It's also linked to other conditions, including cardiovascular diseases. And so birth weight is an indicator of future health. So the question that I always had is if toxic environmental factors during pregnancy contribute to low birth weight. And actually, to do so, we use a small cohort of child-mother pairs, and we have also detected metals in maternal urine during the second trimester of gestation. All these chemicals were considered toxic, and they are strongly correlated with each other. And of course, we have birth weight at delivery. So what we have done is to understand their relative contribution to the mixture, so their detrimental effect. And as you notice here, lead is extremely detrimental for health. And also, once we understand that, we can combine all this information in one single index that can be represented on the x-axis, and then on the y-axis we have the birth weight. As you can see here, we see that there is for one increase in the index, the mixture index, we have a decrease in the birth weight. So, and this is strongly significant. One thing is, in this case, we use an informative prior, so now you know what it means. Okay, so we also developed the R package to facilitate the application and improve reproducibility of our work. And it's available online on my GitHub repository. Future work, definitely, we need to extend our work to high-dimensional data and to multiple time points, and this increases complexity. So we actually need more data to create those type of models. We have to, for sure, as a field, we have to increase reproducibility, and so invite people to have a public repository and also publicly available data. Those are extremely important for all the scientists, and I think we can move forward towards that direction. I have here a lot of information where you can find more information about Bayesian, especially linked to coding skills that you can improve. Like Jeff mentioned R, I usually R and N. JAX is also available, and it's very nice to work with that. There are several tutorials online that you can follow. I think there's no a common route for this type of analysis. You can come from a different field and learn how to do these things. It's a very fast-paced field, so definitely you have to be ready to adapt and to code in different languages at the same time. And thank you so much. I was extremely brief, but I'm happy to take any other questions.
Thank you, Elena. That was really good, and we learned a little bit of some things that you do as well from this presentation. So it was also very nice. So so please feel free to ask your question for Elena and Jeff now. You can write your questions in the chat, and we'll basically convey it to them. So just to have the ball rolling. So this is a question for both Elena as well as Jeff. So maybe Elena, so you can go at first. So let's say you have a project in mind, and you want to basically want to start it. So what's the first step? The first step is to get some data sets to essentially find the problem. How do you go about doing this in your case?
Actually, I want to say that there are a lot of publicly available data sets that you can use. One of the data set that is widely used is the NAINS data set that you can find online, and has a lot of data, I think from 2009. And this can be helpful to train any type of model first. So then second, depends on the research question, I think. The research questions is a big problem because you have to have a very narrow question. So you want to understand a little bit more of something. I don't know, maybe birth weight, and you want to link, I don't know, to jelly beans. So in that case, you need to find a data set that has both informations. That can be also tricky, but once you find the data set, and then you can create a different approaches, different models on it. Actually, you can start applying the models that you have. And once you don't find the right model, then you can start creating the model. In that case, there are several, this is my opinion. Start with the things that are already available. So models that are already available. And then if nothing is available for that specific research question that you have, you can maybe talk with others, or maybe can develop something new. Jeff, this was a very difficult question.
No, this is a really difficult question. I think generally speaking, I sort of describe the data science process as beginning with formulating some question that you're interested in. And I think from there, that you either have to figure out whether or not that question can be answered using some data that you already have, some data that a collaborator of yours might have, some data that you might be able to find online. And that's not always an easy process. And I sort of mentioned that you have to be able to keep track of like understanding what happens in your data set and whether or not that is well suited to answering the questions that you're interested in. And that's sort of a data literacy sort of a problem. But I guess sort of more specifically, how would I go about finding some data sets? I would start, if it's the kind of question that can be answered without using patient data. For a lot of the work that I do requires patient data. If it doesn't require patient data, I would start by Googling, and I would see whether or not there is some publicly available resource. I would see whether or not there is something that I can access through like an API, or maybe I need to download a spreadsheet or something like this. I think that's where I would go to sort of start out finding some data. Yeah, it's a tough question, but I think that's where I would get started.
Thanks. So, okay, so we have some questions from the audience. So first is, I think it's so what type of personality or personal trait best suited for data science study or career? Who wants to answer?
I mean, maybe I said that, maybe I didn't explicitly say that, but there are several data scientists. So data engineers are behind the scenes. So they are often not that outgoing, so they are not extrovert most of the time. I don't want to generalize too much because it's not always the case, but the personality, I mean, everybody is needed in this type of field because it's very heterogeneous. So we don't, so everyone can contribute. And everybody has a talent, just has to find the way to express it, and that's it. I'm actually very shy. I'm actually very shy, but I force myself to do so to present. So I don't know.
Yeah, I agree that I don't think there is any sort of one personality type that is best suited to doing data science. I think if there were if I had to pick a single trait to say is important, I would think that it's sort of curiosity more than anything. And from there, a willingness to learn the tools, the techniques, the substantive area, whatever it is that is necessary to make a contribution to answer a question. I think curiosity is sort of the most important piece of that puzzle. And learning the technical skills is something, you can do as long as you're willing to and you're engaged in that problem.
Okay, so there is some other questions. So in business research, journals are focusing on p-values. How can we convince reviewers that confidence intervals are more relevant? This is a little bit more technical.
Yeah, I'm sort of shaking my head, because if you can figure that out, you would solve an awful lot of problems in an awful lot of domains. I think I guess sort of my perspective is it would be great if everybody was using confidence intervals. I think p-values are so established now that it's sort of going to take a concerted effort on the part of educators to train sort of a next generation of folks who are interested in having confidence intervals, and then to have enough of those folks out in substantive areas to be asking for things other than p-values. I don't think p-values are just going to sort of go away without an influx of folks who recognize the potential shortcomings of p-values in a variety of circumstances. I'm not a fan of p-values, and I still report them in the papers that I write. It's just sort of a fact of life when you're doing this kind of thing, I think.
I say something on p-values.
Yeah.
I think the problem is not having a p-values. I think the problem is that we are using a dichotomization of something that was constructed as continuous. So if we consider p-value as a cutoff of 0.05 and 0.051 is considered bad, but it's so close to 0.05. So the problem is the fact that we are dichotomizing it. So if we are can use it as a continuous value, then I think we can use it in a proper way. That it's a different way. We don't want to demonize the p-value itself. It's very useful, I think, in general, if used correctly.
Okay, so moving on. So we have another question. So this is related to large data sets. So in general, how important would you say time complexity is? And is there any way to get around long run times for analysis? If any of you have a magic answer to that, please do let me know.
I guess, you know, I feel like this is going to be a harder question for Elena to answer, because as a Bayesian, Bayesian approaches are just sort of inherently more computationally demanding. So I think, how would I answer this? I think often computation time is not the hardest or most time consuming part of doing a reasonable data analysis. And if it takes the right model a few hours to run, usually that's okay. If it ends up being a case of that's too long and we really can't wait, then the first suggestion that I would have is to ask whether or not the model that you are running is absolutely necessary for the application that you're interested in. I think in the context of big data sets, sometimes very simple approaches are sufficient to answer the questions in a way that is all you need to actually answer the questions. And the simpler the approach, generally speaking, the faster it's going to run. You know, I guess sort of the bottom line is, if you can't use parallelization, if you can't use put everything onto a GPU or a cluster or something like this, then like the computation time is just going to sort of be what it is, and you have to decide whether or not that's worth it in the overall data analysis pipeline.
Thank you, Jeff. I think that was a good one. Okay, so I'm going to combine the last two questions together. So is data science, or part of the data science, underappreciated, overappreciated, or just plain old hype?
Elena, do you want to take a stab first?
You can go.
Sure. So I guess my feeling is, whether or not data science is hype, I don't think so. I think that, sort of as I said, a lot of the early reaction to data science was understandably that it was rebranding some existing skill set in a way that was, you know, in the most cynical view, creating new degree programs and new majors for universities to attract students. And I don't think that is a fair representation of sort of what I think data science actually is. I think that there have been, for a long time, folks who are interested in doing useful work with data in a wide variety of disciplines, but as I sort of mentioned, the connotation of doing data science, I think, shifts a perspective in a way that isn't either trivial or simply hype or a marketing term. And I guess sort of one concrete example that I would give is that many of the folks who I know, and this is definitely sampling bias, but many of the folks that I knew who gravitated towards data science early were applied statisticians who didn't feel that statistics, as it was traditionally defined, really represented the kind of work that they did. That it didn't really appreciate the extent to which they were involved in understanding a problem in context, and working with data in a principled way, in coding well, in disseminating results publicly. And that certainly those are all things that applied statisticians maybe had done in the past, but it wasn't really recognized as useful or important work in that discipline. And so I think the emergence of data science absolutely draws on a lot of skill sets that have existed for many, many years, but also it represents something that I think is new and different and important.
Okay, so I think we will ask our few final questions. So is there any underappreciated approach within the data science worth learning? I think this goes back to some of the stuff that we were talking before.
I think for me, in my case, especially with my perspective, probability is totally underappreciated, but it's so important, especially for constructing models. So definitely something worth learning. I know that it's very extremely challenging at the beginning, but once you study, you never go back. So it's life-changing, I think.
Yeah. Sorry, I don't mean to interrupt. Go ahead.
Please.
So I think if I were going to suggest that there are, well, I think underappreciated approaches, I think I have two answers to that. The first is that traditional methods, I think, are sort of paradoxically underappreciated in data science. That I think there are a lot of folks who are looking for the next new big thing and are focused on deep learning or AI, when, as I said, a lot of the times you end up doing linear regression or calculating a mean or something very, very simple. So I think sort of paradoxically, the underappreciated approaches are sort of foundational kinds of things that really need to be understood and used in appropriate circumstances. Now, that said, I think there are some exciting developments at sort of that real cutting edge of what's possible in deep learning and in AI. I think there are versions of those neural networks that require smaller training sets that borrow information across different models that you wouldn't think and turn out to be useful. I think that seems like an area where there is some real potential to get the benefits of an AI approach without the computational and big data demands that are usually come up in that sort of an area.
Okay, so all right, I think we are over time. So thank you to both Jeff and Elena. It was really wonderful, and I think through both of your presentations, we have learned basically some very nice definition of data science, how you apply, what platform you use, and how do you go about essentially starting from using open source data sets to building your model and building your portfolio. So thank you all. Thank you for coming, and let's thank our speakers. They've done a tremendous job, and yes, hopefully you all have a great night. And thank you all. Take care.
Thanks, everyone.
Bye.